We'll now talk about the concept of zero-point energy and how we calculate this. So first of all, what is zero-point energy? Well, we need to think a little bit about vibrational energy and energy levels in general. And it turns out that the vibrational energy in the ground vibrational state is actually non-zero. So that's rather special about vibrations. But for example, in the harmonic oscillator potential that we'd have here, we have a zero level, and this particular zero level has a value of 1/2 h bar omega. So in general, the expression for our harmonic oscillator, the energy levels, have this value of n, where n is the quantum number, plus 1/2 times h bar omega. So then even when n is equal to 0, we've got this 1/2 h bar omega. And so we need to account for this because that means that even at 0 Kelvin, all of our molecules are vibrating. And so they've always got this bit of vibrational energy that we need to treat. Now we can determine what this zero-point energy is. Basically, we'll take all of these different zero-point energies for all of the vibrational modes of the molecule and we'll add them up. And so we'll just sum over all of our vibrational modes. We'll have this 1/2 h bar of omega I, where that's the frequency of mode I. And I wanted to mention that I often refer to it as zero-point energy, but you might see it called zero-point vibrational energy. So you might also see the abbreviation of ZPVE. Now, when we think about a molecule at 0 Kelvin, we can determine its internal energy as being a sum of the electronic energy plus this zero-point energy. And so the internal energy at 0 Kelvin is the sum of these two terms. I also wanted to mention that the frequencies do depend on the mass, so the zero-point energy is going to end up being isotope dependent. So if you're comparing with experiment, we really want to think about the full isotopic distribution of that experimental collection of molecules. Typically what we'll do in calculations is we'll just think about the most common isotope, but if you are trying to compare really accurately with experiment, you're going to need to think about those isotopes. Anyhow, it does depend on the mass. All right, now why do we care about that? Well, the zero-point energy can end up affecting different things we're interested in, like isomer energies or reaction energies. So for example, the reactants and products might end up having different zero-point energy values. In this example here, for example, maybe our reactants have a very steep potential well. They've got a lot of zero-point vibrational energy. Our products might have a shallower well. They've got less zero-point vibrational energy. Well, what we're going to do is we often have been computing something like delta E electronic, but we really want this change in energy between the actual levels of these molecules. And so how do we do that? Well, this delta U0 is really just the products minus the reactants. And we can think of the energy of the products as being the electronic energy plus that vibrational energy, the zero-point vibrational energy for that particular species. And then we can subtract off the same thing for the reactants, the electronic energy of A plus the zero-point energy of A. So we have this expression here. Well, now we can rearrange it. We can gather C and A together, and we can gather the ZPEs together. So we'll have an expression that looks like this. Well, this, our first term, is just our delta E electronic that we can compute just from the electronic energies. Our second term is the difference in the zero-point energies between these two species. I should say it's not, I was pointing out this, but it's not really that. It's the difference between this energy and this energy. But overall, once you have your delta E electronic and your difference in your zero-point energies, it gives you this delta U0. All right, another example where we really want to think about something like zero-point energy could be dissociation. So if we talk about something like a diatomic, here's our equilibrium distance and our dissociated distance is out here. We can talk about two different dissociation energies. So if we talk about DE, DE is measured from the very bottom of this well to the dissociated limit. On the other hand, D0, which is what you'd measure experimentally, that's measured as the energy difference between the dissociated limit and the V = 0 limit. Here we're using V equals for the quantum number. So we do need to account for that difference when we're thinking about dissociation energy, which dissociation energy is meant in a particular context. All right, so let's think about just a couple of examples. So let's set up these energies and these 0-point energies for molecules A, B, and a dimer A2 and answer the 3 questions. First of all, what is the reaction energy, the delta E electronic, for the reaction where A turns into B? What is the 0-point corrected reaction energy for A going to be? So including the 0-point energy. And for dimer A2, what is the dissociation energy from equilibrium versus what is the dissociation energy when you include 0-point energy? So now might be a good time to turn off the video and do the calculations and see what you get. All right, so now let's talk about what we do get. So for this reaction A going to B, delta E electronic is the products minus the reactants. So we can just plug in our numbers that we have up above. That's 0.1 AU multiplied by our conversion factor. We'll get a value of minus 262.6 kilojoules per mole once we do our rounding to significant figures. Well, we can take that value to figure out the 0-point corrected reaction energy for A to B. So first of all, let's figure out what delta ZPE is. So we're given the ZPE of B and A, and so the difference then in those is just 10 kilojoules per mole. Now if we calculate delta U, again, that's delta E electronic plus delta ZPE. We've calculated our delta E electronic up here. We've calculated our delta ZPE. And then we can sum those together and we get a minus 252.6 kilojoules per mole. And we can see that that 10 kilojoules per mole, that can make a difference in our reaction energies. So we want to be able to account for that. All right, let's think about the dissociation of dimer A2 into 2 A's and ask the questions again. What is DE? What is D0? Well, DE is going to be our products, which is the 2 separated A's. So 2 energy of A minus the energy of our dimer. So we can plug in our numbers for our energy of A, our energy of our dimer, and we'll get a positive value of 1/2. Think about that. It takes energy to dissociate something. So, okay, positive is a good thing. Multiplied by our conversion factor, we've got 13 kilojoules per mole. Now we want to account for the 0-point energy and figure out what would we measure. So again, D0 is going to be DE plus that delta ZPE. So here we've got our value with all available significant figures. And then we'll take our delta CPE. So we've got 2 times A again, minus A2, 44. So overall, this works out to be a minus 4 kilojoules per mole. And so it's really, we end up with a value of only 1309 kilojoules per mole for our D0 value. So in this case, fairly close, but you can potentially measure that difference. Okay, so now let's talk a little bit about scaling frequencies and why we would want to do that. Well, normally when we calculate our frequencies, we're using a harmonic approximation. So we use the second derivative of our energy to calculate our force constants and our frequencies from that. But the thing is, the real potential well, such as the one shown here for a diatomic, is actually anharmonic. And so this blue curve is anharmonic, and you can see that it spreads out. It's a bit wider, really, than the harmonic. And so when we calculate the frequencies, the anharmonic frequencies, such as this B equals 2 one shown here, they're really usually lower than the corresponding harmonic frequencies. So those anharmonic frequencies are lower. So one thing that you can do is to scale the frequencies and the corresponding 0-point energy, to scale them by a scaling factor. And this scaling factor will account for the anharmonicity in the well. It also accounts for insufficiencies in our level of theory. So for example, Hartree-Fock usually creates even the harmonic potentials are already too steep. And so it'll also account for the fact that the level of theory has some errors in it as well. So just a few examples. If these are all using the same basis set, B3 lip, you have a scaling factor of 0.96, MP2 0.94, Hartree-Fock 0.90, because again, it was really too steep, so the values were much too high. And so what you'd do is you'd calculate your 0-point energy at some particular level of theory, and then you'd scale it by this factor prior to putting it into your energy expression for your reaction energy. All right, so just a few things. It's actually pretty straightforward to calculate these ZPEs. So of course, what we need is an optimized structure. Frequencies only make sense when we're dealing with optimized structures where the gradient's equal to 0. Of course, we're going to need the energy at that structure. That gives us that electronic part of our reaction energies. And then we'll need vibrational frequencies for that structure. So basically, once you have an optimized structure, you can calculate your vibrational frequencies, and then you can use that to calculate your 0-point energy that you can add in to your electronic energy. Now, a couple of considerations. So the 0-point energy is dominated actually by the high frequency vibrations. So you might ask, why would that be? Well, we think about our equation, and we're dealing with the sum over all these vibrational modes. Well, the high frequency vibrations just have higher values for this frequency. And so we end up seeing that ends up dominating the value we get for our ZPE. On the other hand, though, our equation for calculating entropy ends up actually being dominated by the low frequencies. And so that means then that small errors in the low frequency modes can actually lead to some fairly large changes in predicted entropies. And also the harmonic oscillator approximation is just not as good for some of the low frequency motions. So overall, then that means that the errors we get in entropy are going to end up being larger than the errors that we get in 0-point energy. So when we calculate things like enthalpy or internal energy, those are going to essentially have more significant digits than, say, the free energy calculation, where we'll have a little bit more error because of that entropy. So anyhow, I hope this is a lot of very useful information about the 0-point energy and everything that we can think about related to this particular thing when we're calculating reaction energies.